I'm Stefan Balauca, and this is our work. Gaussian loss smoothing enables certified training with tight convex relaxations, published in Transactions on Machine Learning Research. This work is a collaboration between the INSAIT Research Institute in Sofia, Bulgaria, and the SRI Research Lab in ETH Zurich. I will start the presentation with a quick introduction on adversarial and certified robustness for neural networks. In standard classification, we have an input like this dog image passing through a classifier that gives a numerical output that we can translate into a hopefully correct answer. However, recent work has shown that neural networks' outputs are vulnerable to imperceptible perturbations in the input. For example, by adding some carefully crafted but imperceptible noise to this dog image, the network can misclassify it. The goal of certified robustness is to formally prove that each possible perturbation in the neighborhood of the input is mapped by the classifier to the correct class. This is crucial for deploying models in safety-critical systems like medical devices or autonomous vehicles. While in theory we can compute this exactly, the costs grow exponentially with network size. In practice, we use much cheaper approximations. The first approximation used for adversarial training searches for adversarial samples that would maximize the training loss in the neighborhood of the input through projected gradient descent. This sample under-approximates the worst-case loss and is used to train empirically robust classifiers. On the other hand, we can opt for over-approximating the loss by computing relaxations of the reachable set. Certified training uses this over-approximation of the worst-case loss for training and induces more regularization in the model, which leads to easier certification. For a comparison between the two approaches, we have first adversarial training, which uses an under-approximation of the worst-case loss, induces low regularization, and trains models which maintain high natural accuracies and are empirically robust. However, usually the robustness of this model cannot be formally verified, and they can still be vulnerable to a stronger, more complex adversarial attack. On the other hand, certified training uses an over-approximation of the worst-case loss, which trains highly regularized models with high certified robustness, but at the cost of decreased natural accuracies. Next, we discuss about the main motivation of our work, the paradox of certified training. First, to illustrate the issues, let's consider a simple task. We need to prove that for this toy network, we have z greater than or equal to 0 for all values of x between -1 and 1. The most basic method for verification, box or interval arithmetics, which is also the most widely used method in certified training, fails to solve this task. We see that the input node x is bounded by the interval -1, 1. Using the rules of interval arithmetic, the two hidden nodes will also be bounded by -1, 1. Finally, the bounding interval for z will be the sum of the hidden nodes, which is the interval -2, 2. However, it is clear that the output is always 0, as the actual value of z is always x minus x. The problem is that using interval arithmetics, we over-approximate the bounding for linear layers, and we assume independence of hidden variables. A solution for this problem is to use tighter, more expressive relaxations instead of interval arithmetics. There are a number of proposed relaxations for propagating the reachable set of points through a classifier. However, the better approximations usually come with increased costs, making them infeasible for training. A compromise is to use intermediate precision methods such as zonotopes or deep poly, which only have quadratic complexity but good approximation quality. In practice, when comparing the ability to verify different relaxations for the same network and the same inputs, but with varying size of the neighborhood, we observe a clear trend where tighter relaxations are able to verify more samples at higher perturbation radii. From these observations, Jovanovic et al. Introduced a score to measure the empirical tightness of convex relaxations based on their verification power. In theory, since tighter relaxations can verify more samples, it follows that the loss over approximation of tighter relaxations should have lower values, therefore lower penalties and regularization, and, eventually, better overall performance for certified training. Unfortunately, multiple studies have found the opposite. When using tighter bounds for training, performance is often worse than with loose relaxations like IBP. This phenomenon was named the paradox of certified training. Jovanovic et al. Have analyzed this issue and have concluded that the lower performance of certified training with tight relaxations can be attributed to harder optimization problems caused by the discontinuities and high sensitivity of the loss landscape generated by these tight relaxations. In this work, we propose a solution for solving these issues, Gaussian loss smoothing. We propose to correct these problems of the loss landscape of tight relaxations by applying a Gaussian kernel over the loss function in the parameter space of the model. In practice, we instantiate Gaussian loss smoothing, short GLS, with two algorithms. PGPE, a zero-order approximation optimization algorithm that estimates gradients by sampling the loss, and RGS, a first-order optimization algorithm that computes the average of the gradients in the vicinity of the current parameters. We can see in this figure how sample-based smoothing can change the loss landscape of IBP, crown MPP, and deep poly. The PGP algorithm works by sampling pairs of symmetric perturbations around the original parameters. For each pair, we evaluate the loss difference. Finally, we compute a gradient estimate as the sum of perturbations weighted by their respective loss differences. PGP has the advantage that we only sample the loss values, so there is no need for a backpropagation step. This leads to lower complexity and memory footprint, while also enabling the use of new non-differentiable loss functions. On the other hand, PGP needs large sample sizes to produce qualitative estimates, so it is infeasible for deep architectures with thousands or millions of parameters. The RGS algorithm performs smoothing directly over gradient samples. We first sample perturbations around the central point. We compute gradients for each perturbation using standard backpropagation and then average these gradients to obtain the RGS estimate. The main advantage of RGS is its ability to work with even very small sample sizes. 2 samples still works well. This makes it a good option for scaling to deeper networks and more complex tasks, where we expect the effects of tight relaxations to be even more pronounced. On the other hand, RGS does not benefit from the theoretical guarantee of converging to the exact gradient of the smooth loss function. Now, let's look at the results of our experiments. First, we prove that GLS, as instantiated by PGPE or RGS, achieves the expected performance ordering between loose and tight relaxations. With standard gradient-based optimization, the loose IBP gets the best certified accuracy, but when applying loss smoothing, we obtain the expected correlation between tightness and certified accuracy. Second, as stated before, PGPE works without direct gradient computations, and therefore can be applied to even non-differentiable relaxations, such as alpha crown. We successfully trained small networks using PGPE plus alpha crown, and we obtained a performance improvement over PGPE plus deep poly. While PGPE, especially when combined with alpha crown, is very computationally expensive, the performance gain might be worth for the cost for safety-critical applications, where only small networks need to be deployed, such as embedded medical devices or air flight control. It is important to mention that PGPE only impacts the training costs, as the inference is exactly the same for certified models. Third, we managed to scale GLS training to deeper networks and more complex tasks using RGS. We observed that deep poly plus RGS obtains better certified accuracies compared to the state-of-the-art methods using the same 5-layer CNN architecture. The performance of deep poly plus RGS is even comparable with the standard IBP-trained 7-layer CNN network, a model that's 10 times larger. These results validate the assumption that the over-approximation effects of loose relaxation become more pronounced for deeper networks. Finally, a few takeaways from our work. We verify for the first time that tighter relaxations can obtain better results in certified training. We demonstrate both theoretically and empirically that Gaussian loss smoothing can mitigate the optimization issues associated with the paradox of certified training. For the first time with PGPE, we managed to train a certified network using alpha crown, a tight but non-differentiable relaxation. And we demonstrate that the advantages of using tight relaxations for certified training scale to deeper networks and more complex tasks when using RGS. We hope that our work will inspire further advancement in certified training. We consider it is of great importance to further reduce the computational costs of certified training with tight relaxations. For more details, please check our paper and code in the video description.